Okay, let's try this. Let's see, we have a 0.50 kilogram mass that is suspended from a spring. That is a horrible looking spring, sorry, but it is what it is. So, and it vibrates 3 times per second. So it's got a mass of 0.50 kilograms. 3 cycles per second is a frequency, which is 3.00 hertz. Okay, and it has an amplitude of 0.15 meters, so it goes up and down, maximum of 0.15 meters, so from its rest position, 0.15 meters. Okay, so let's see, what do we have to do here? We determine its speed when it passes equilibrium position, which is here. Okay, velocity when it's this far from equilibrium, total energy of the system, and the equation describing the motion of the mass, assuming its position is a maximum when t equals 0. Now, calling position maximum is kind of poor, but or kind of not great terminology. But what they mean is that at t equals 0, its position is right up here. So at the very top of its peak. So at t equals 0, x, or actually let's call it y since it's suspended. So y equals the maximum position it has, and the amplitude is the maximum displacement it gets from 0. So this position here is y equals 0, and this position here is y equals plus a, capital A for amplitude. Okay, and what this means then is that we want to pick a trig function that gets us a value of 1. So y is going to be a times some trig function some trig function of omega times t. And when t equals 0, this whole thing in here is 0. So what trig function, we can choose sine or cosine, what trig function gives us 1 when t equals 0? And the answer is cosine. So what works here is y equals a cosine omega t. And then we just have to recall that, of course, we already have a here. And so we can go ahead, we want to write in a equals 0.15 meters we can, or however we want to do this. Omega is 2 pi times the frequency. So let's see, that's going to be, the frequency is 3.0 hertz. That's going to be 6 times pi, which is like 18.84-ish, so about 18.84, yeah, so about 18.8-ish radians per second. And so you can either write that in for, you can either plug those numbers into your equation or whatever. I'm just going to leave it like this and say, because this tells us everything we need to know. That's not part A, though. That is part D, because we decided to do part D first. So D is done now. Okay, total energy of the system. Now this is not quite perfectly phrased because total energy really depends on where you set your potential energy equals 0. So for this, I'm going to assume potential energy equals 0 at the equilibrium position, which we're saying is y equals 0. That's generally what we do with these things. Okay, so I'm going to do part C in green because I feel like it. And let's see. So the total energy of the system, is kinetic energy plus, that's not total energy, sorry. Total energy, or the mechanical energy of the system, is potential plus kinetic. So our choices are either we can find V, well, kinetic is 1/2 mv squared, and for potential, we use 1/2 kx squared, or 1/2 ky squared. And the tricky thing about this is that this includes gravity if you measure y from the equilibrium position of the system, which is not the rest position of the spring. So if you use y measured from the rest position of the spring, you have to also include mgy for the gravity term for potential energy. But if you measure it from the equilibrium position of the system, then all you need is this. If you need an explanation, a justification as to why that is the case, I'm not going to include one right now because it's really not germane to reviewing for the test. I'm just going to tell you that that's what it is. So this expression here includes gravity if y equals 0 at the equilibrium position of the system. Okay, so what we can do now is, and potential and kinetic energy are going to change. This is going to go up and down and up and down, up and down. In the middle, it's going to be moving fastest. At the extremes, it's going to be stopped for a moment, but it's going to have maximum potential energy. So the easiest thing to do here is find a time and a place where potential energy is 0, or where kinetic energy is 0. So, what do we want to do? Let's say that we want to make it. Well, what's a good call here? Total energy of the system. Probably the best way to go about this then is we know what m is. Let's see if we can find out what k is. So we can recall from working with energy that omega squared, or not working with energy, but working with simple harmonic motion, that omega squared for a spring mass system is k over m. Okay? And this is, since this is omega squared, and omega, you'll recall, is 2 pi f, remember? So this is 4 pi f squared if you want to use it that way. But really, so the way to do this then is to go k equals omega squared times m. And then omega is 18.8. So this is actually 18.8 squared. So 18.8 squared times the mass of the system, which is 0.50. And let me just pop up the old phone with calculator in it, just like physicists through the ages have used. 18.8 squared times 0.5 gives us 176.7. So k, come on k, there we go. K equals 176.7, and the units on that are newtons per meter. And so then it's pretty easy. Tricky here. So this k here is kinetic energy. So I'm going to put serifs on that to make it a capital letter. And this k here is also kinetic energy. Serifs, capital K. Although now it's just sort of an ugly thing. This is lowercase k, spring constant. Different thing. Okay? So, with u equals 1/2 ky squared here, that's little k, that's for the spring constant. And this is it. And then we want to find u max, so the maximum value of potential energy. And that will be at these extremes where it's not moving, so the kinetic energy is 0. So this is going to be 1/2 little k spring constant times the whatever value of y gives us the maximum value of y squared. And that's going to be when y equals a, or negative a. So 1/2 ka squared. And then, not terribly hard, we could actually go even and symbolically plug stuff in here if we wanted, or not. But what this gets us is that u max is 1/2 times, well, I'll just go ahead and plug it in, 176.7, and then the amplitude is 0.15 meters, so squared, sorry. So answer times 0.5 times 0.15 squared, and that looks all right to me. So u max, maximum potential energy, is almost 2 joules. It's 1.99 joules. Okay, and when u is at a maximum, that's here and here. At those points, kinetic energy is equal to 0. So that is going to be the total energy of the system. Come on. E mech. Okay, 1.99 joules. So that takes care of this guy. Speed when it passes the equilibrium position. Well, in the equilibrium position, let's go for what color? Purple. Okay, fun. In the equilibrium position, which is right here, in the equilibrium position, let's do part A up here. So in the equilibrium position, y equals 0, which means that since y equals 0, potential energy equals 0. So at this point here, this is the point we're interested in part A, potential energy is 0, which means K, our kinetic energy, is our total mechanical energy, which is, some idiot's calling me, alright, is, right, that's our total mechanical energy, which is 1.99 joules. Hope I got space there. That might be off the screen. Anyway, but that's this 1.99 joules is all kinetic when you're at point A, and that means that, let's see if I can erase a little space here, and that means, oh no, okay, well, close enough. Alright, so that means that 1/2 mv squared, which is our kinetic energy, is 1.99 joules, and so v squared is 1.99 joules over 2 times mass, which is 0.50 kilograms. So actually, v is going to be very close to square root of 2, because your 2 times your 0.5, we're going to cancel it there. And so your speed, your maximum speed, is going to be, come on, jeez, come on, piece of crap. Maximum speed is going to be about 1.4, is that right? 1/2 mv, oh no, I put my 2 in the wrong place. Crap. And now my stupid piece of crap thing isn't working. Okay, well the mouse isn't working. So you're going to have to, let's see, come on. Yep, it's decided to stop working. Okay, well I'm going to have to fix my pad, but maximum speed then is going to be, and now the mouse isn't working at all. Fantastic. Alright, so maximum speed is going to be not what I, there we go. Boom, we're back. Okay, sorry. So Vmax is going to be about 2 root 2. So I think we're going to get something like, for A, we're going to get V of, let's see, 2 times root 2 is going to be about 2.83 meters per second, give or take. Okay. Part B is just another energy balance. It's just harder because neither one of them is 0. I'm going to leave that off so I can fix my hardware, but that is, I hope, crying out loud. Alright, that is, I believe, problem 1.